Hi, and welcome back to our series on photovoltaic systems. Let's continue on with our line drawings, part 3. So this is the same drawing we've seen in part 1 and part 2. We've gone over PV modules, home run cables, combiner boxes, DC disconnects. Now we're up to inverters and our choices there, and our AC combiner, AC disconnect, and our actual point of interconnection. We can see by this diagram we have two inverters. So much like a DC combiner, we need an AC combiner. We need to combine the outputs of these two inverters into one source. That's going to go through our production meter, to our disconnect, and to our tie-in. So we're going to parallel these outputs. This is a 240 volt system, so our voltage is going to stay 240. Our current's going to increase because we're paralleling them. The inverter converts the DC power and inverts it to AC. This is what's needed to tie back and to power stuff in your house. So we have our DC coming in, our DC negative, our DC positive, and on our output, we have our hot legs. Line 1, line 2, neutral, and of course a ground. The different types of inverters we're currently using, we have string inverters, primarily in residential and commercial. Typical sizes are 2 to about 36 kilowatts. In commercial systems, string inverters are becoming much more popular as compared to a central inverter. We use this in a 50 to up to megawatt size ranges, large commercial utility scale systems. So the string inverters in commercial systems becoming more popular because say you had a 100 kilowatt central inverter and you had a failure, an inverter failure. Well, your whole system is dead. Your 100 kilowatts is sitting there and it's not doing anything. If you used, say, 4 Sunny Tri-Powers, 24 kilowatt inverters, you have about 100 kilowatts of PV of inverter capacity. If one inverter failed, 3/4 of your system is still up and running. So there's certainly an advantage to using string inverters in commercial sized systems. Then there's microinverters. Enphase is extremely popular. Small, residential, commercial. The advantage of the microinverters is there's one inverter for every module. If you have 20 modules, you got 20 inverters. So if you had shading on one of your modules, only one module would be affected. Whereas with the string inverter, if you have shading on one module, the output of the whole array is going to be affected. So there's certainly advantages to microinverters, particularly in shading situations. You have a lot of trees around, there's chimneys, dormers, whatever. Shading part of the array, one module or part of the array, a microinverter may be the best choice. Similar to a power optimizer, say a solar edge, used in residential and small commercial also, 2 to 36, they have a 33.3 solar edge inverter available now. The solar edge inverter is something between a micro and a string inverter. You use an optimizer, one for every module, 20 modules, 20 optimizers, plus an inverter. The solar edge inverter, for example, using power optimizers, works on a fixed 350 volt input. So stringing these inverters is considerably different than with a typical string inverter, say an SMA or Fronius, because they work on a fixed voltage. The thing that varies in the system is the current. The current varies. So if you had a module in shade, the current output from that module will be lessened, but the voltage coming out of the whole string will still be 350 volts and it'll continue to work. Only one module will be affected. So there's advantages, certainly advantages to optimizers with the solar edge system. We have AC combiners. We saw in our illustration, which we have a little cutout of here, we have two inverters. These could be string inverters, which they are in this case, or they could be multiple strings of, say, Enphase inverters. Well, we're going to parallel these together into our AC combiner box. Our output's going to go on its merry way off to the grid. When we're trying to pick out what kind of an AC combiner or AC load center that we need, we have to look at what do we really need. Number of spaces in the combiner box, the AC combiner box. A 612 has space in there for 6 single pole breakers. Typically, when in a residential system, it's 240 volt, so we need 2 pole breakers. So we could fit 2 pole breakers in this box. In a 612 box, we could fit 3 2-pole breakers. We have to look at the bus rating of this enclosure. We have to match the voltage rating of the device. So if we have a 240 volt, we want a 240 volt combiner box. If it's 3-phase 480, we need a different box. 240 volt residential box is not going to work in a 3-phase system. What is the NEMA rating of the box? A type 1 is an indoor rated box. Can't be outside. It's got to be enclosed somewhere like in a garage or someplace. A 3R, which is good for outdoor, or a 4X, which can be mounted horizontally. We also want to look at how you're going to connect this. You got main lugs and main breaker. Main lug is probably the most common. That's what we showed in our illustration, a main lug box. MLO, main lug only, means there's no main breaker. You only have your branch breakers from the inverter to your tie-in. And then the overcurrent protection. How big is the breaker going to be? So when a string inverter, we're going to look at it and say, what's our maximum output of the inverter? Not how many modules are on it. Nobody cares about that at this point. The utility and jurisdiction is going to want to know what is the potential output of that inverter. You take that output of the inverter, you add 25% for continuous duty. There's your number. Very similar to N-phase. Say you're using N-phase. The number of inverters in a branch circuit times the inverter maximum output plus 25% will give us our number to make sure that we don't put a box in that's undersized and going to cause a problem. So our system descriptions, in this case, we have a square D box. It's a QO. It's a QO low center, 612. We can put 3 2-pole breakers in here. It's a 100 amp box. It's good for 120, 240 AC. It's a 3R box, so we can mount this outdoors. It's main lug only, so there's no main breaker. And here's the manufacturer's part number. If you're going to use a QO, square D QO box, you have to use QO breakers. So the breakers have to match the enclosure, or they won't fit. So we're going to tie this in. There's a couple different ways that systems can be tied in, and what kind of disconnect that you're going to have to use. A load side connection, really typical load side connection. There's your main service panel. These are all your load breakers going out to your, bedroom and living room and refrigerator and whatnot. So we're tying into there. We're tying in at the opposite end of the bus bar from where the feeders come in. Our feeders come in from the utility, from the top, which means we're going to mount our breaker at the bottom. If it was the other way around and the feeders were coming from the bottom, we would mount our breaker at the top. So opposite end of the feeders. How much can we backfeed into this? There's a question that comes up all the time. So our maximum overcurrent protection device, a maximum breaker size that we can backfeed according to code, is we take the bus bar rating, say it's a 200 amp panel, times 1.2, add 20% to it. So we got 200 amps plus 20%, and then we minus the main breaker. So if we had, say, and typically you have a 200 amp service, you have a 200 amp main. So we take our 200, that's our bus rating, plus 20%, minus the main breaker, minus 200, it equals 40, right? 200 plus 20% is 240, minus the main breaker, which is 200, leaves us a remainder of 40. The maximum backfed breaker we can have on this system is 40 amps. In this case, because we have fusing here, our breakers right here, consider fusing, that we don't need to have a fused disconnect. All we have to do is disconnect it. Some jurisdictions really want this. Some say this breaker is good enough. Tough to say, depends where you are. The fusing is there not to protect this device or anything downstream, our inverter or anything else. Overcurrent protection is there in cases like this to protect the wire. If you have a 40 amp breaker, you have to have wire rated for at least 40 amps. So the wire can't overheat and potentially start a fire. You can do a supply side connection or a line side, as it's called. It's a parallel service from the utility. We still have our utility. We have pretty much the same panel board. We have our meter, but we're not tying into a breaker. We're tying in between the meter and the main breaker. That's where we're going to make our parallel connection. In this case, from our connection to our disconnect, there's no overcurrent protection device. There's no fusing. We're tapping right in before any of the breakers. So we need to have a fused disconnect. Something has to protect this wire. That will be these fuses right here, the little squiggle lines. So it's a fused disconnect. Hope that makes sense. So our AC disconnects, and we want to disconnect our inverter, our system from the utility. So we're going to put this in, or a visible blade disconnect, as some jurisdictions want to call it. So they can open this cabinet when the switch is in the open position and see a visible disconnect. Not a breaker or anything like that. Some places just want to see a visible disconnect, in which case we'd use a device like the Square D disconnect right here, non-fused. We have our overprotection right here. In our AC disconnect, what size do we use again? Well, we're still back to the number of inverters we're going to parallel. In our case, we had 2, times the output current of each inverter. Right, so we're going to have 2, and if it was 10 potential output, well, it'd be 20, plus 25%. Back to the 25% for continuous duty. Number of poles, this is a 2-pole, because we're doing it with a split phase system, 240 volt, 120, 240. If it was a three-phase system, we'd need a 3-phase disconnect. Whether you need fused or unfused, another question. For a load side, where we're tying in on the load side of the service panel, protected by a breaker, we use an unfused disconnect. Our overcurrent protection is the breaker that's in the main service panel. On a line side, because we're parallel on this, as we talked about just a moment ago, there's nothing there to protect the wire. So we need a fused disconnect in a parallel service. And it's the same thing, the fuse rating, number of inverters, maximum current of each inverter, plus 25%. If we look at this illustration, we can see this is a fused disconnect. The black line is line 1, red is line 2, our neutral, which you can't really see here because it's hidden under these wires, our neutrals are tied in there. Green is our ground wire. These are our inputs from our inverter. These are our outputs. And in this case, these cartridge fuses right here, this is an illustration or photograph of a fused disconnect 2-pole. So it'd be a Square D AC disconnect. It's a NEMA 3R. It's an outdoor rated device. Good for 30 amps, 240 volts, 2-pole fused. And this one has a neutral bar and the Square D part number. So I think we went through most everything on here. We started with PV modules. We talked about home run cables, DC combiners, DC disconnects. We've gone over inverters, AC combiners, because we have to combine our 2 inverters here. We came through our production meter to our AC disconnect and off to our service with our service connection and off to the utility. So I hope all this made some sense, and thank you for attending, and we'll see you soon.